Homework 11, Polynomial Functions, Video 9. We're going to do an example of a function I believe we saw earlier and show you everything we can figure out before we sketch the graph. We're going to let h of x be 18x to the second power minus x to the fourth power. And I've got 6 things listed here. It only looks like 5, but when I got to the end, I realized I left one out. So it's part A, point 2, if you will. So let's start with part A. Is this function odd, even, or neither? What symmetry does this imply? Wait, what? We haven't talked about that in quite a while. I know, but when we talked about it previously, and I'm trying to remember if it was in a video or in a reading module, I mentioned that being odd or even is something you can take advantage of when you're graphing. If you're an even function, that means you have y-axis symmetry. Your left half is a mirror image of your right half. If you're an odd function, you have origin symmetry, which means you can rotate the left half to get the right half and vice versa. So we're going to figure out if it's odd, even, or neither. And just a quick reminder, you're an even function if f of negative x equals f of x, and you're an odd function if f of negative x equals negative f of x. Or the way I discussed it previously, you're even if putting in a negative is the same as putting in a positive. You're odd if putting in a negative is the opposite of putting in a positive. So let's put in a negative x and see what happens. So we're going to go to the function, replace each x with a parentheses, and fill in the parentheses with a negative x. So there's 18x squared minus x to the fourth, except each x becomes a parentheses, and now substitute the negative x. And let's see what happens to the negatives. An even power will turn a negative into a positive. Both of these powers are even. So the negative x, when it gets squared, will just become a positive x squared. So we have 18x squared minus, now be careful here. The negative x to the fourth will become just x to the fourth, preceded by a subtraction. Isn't that the original function? It is. Therefore, the function is even, and that implies that there is y-axis symmetry. So now I only have to graph half of the graph, and I can reflect it to get the other half. So even and y-axis symmetry. Every time we get something on the right, it has a mirror image on the left and vice versa. The part that I left out was the number of turning points. That's the degree minus 1, or the most number of turning points, I should say. Since the degree is 4, that means there are at most 4 minus 1, which is equal to 3 turning points. And remember what I said in a previous video, if it's less than 3, you lose them in pairs. So it's either 3 turning points or 1. To determine the end behavior, we just have to analyze the leading term. We had already analyzed this leading term previously, but just a reminder about the gimmick I showed you if you choose to use it. The negative leading coefficient means the right falls. The even degree means the ends are equal. That means both ends fall. And at this point, I'm going to start drawing some things on the graph. Because both ends fall, I'm going to draw 2 arrows pointing down in quadrants 3 and 4. That doesn't mean those are part of my graph. Those are just reminders that both ends are going to point down. Calculating the y-intercept is easy. All we have to do is substitute 0. I just smashed my thumbnail. And if we substitute 0 into this function, h of 0, 0 minus 0 is 0. So we have a y-intercept at 0, which is also an x-intercept. So when we find the x-intercepts, we should expect that 0 is one of them. Okay. In order to do part D, which is where all the work is actually going to happen, I'm going to erase the parts above it if you need them. Pause the video and write them down, and you can always replay the video. Remember, we have y-axis symmetry. I should probably document this. y-axis symmetry, and up to 3 terms. All right, let's calculate the zeros and their multiplicities. Remember, a zero is just a solution to the function equal to 0. So in order to do this, we need to solve 18x squared minus x to the 4th is equal to 0. Now, this is not a quadratic equation. If you're on your A plus game, you might recognize that it's quadratic-like. We could use a substitution. But we're not even going to go there. We're just going to factor this by first observing that this is not what I wanted. I'm going to make one minor change. That's not going to affect anything that's already happened. You'll see why in a moment. The negative x to the 4th was supposed to be negative 2x to the 4th. Now we could do it as is, but I want it to be a little bit more cooperative. It won't change the y-axis symmetry, it won't change the number of terms, and it won't change the y-intercept. So luckily, very minor damage control. Now, to solve any polynomial equation, you can always consider factoring. These have a common factor, a greatest common factor. They both have a 2 in common. Well, now they do. And they both have at least a pair of x's I can pull out. So if I divide all the coefficients by 2 and lower all the powers by 2, I get 9 minus x squared. And the reason I wanted the 2 there is so that we would have a 9 here. This is a difference of squares. It factors into 3 minus x and 3 plus x. And now I can get all of my intercepts, all of my zeros. If I solve this one, I'll get x equals negative 3. If I solve this one, I'll get x equals 3. And this one's a little bit weird because it's not in parentheses, but if you were to put 2x squared equal to 0, you would divide both sides by 2 and get x squared equals 0, then hit it with the square root. Don't forget the plus minus, but it's just 0, so I don't need the plus minus. But the short version of all that is if you have a factor that has an x but no constant added to it, then it's always going to give you x equals 0. But don't forget multiplicities, which I'm going to abbreviate with a capital M. Multiplicity is the power on the factor. Our 3 and negative 3 both came from factors whose powers was an implied 1. So the multiplicity on each of those is 1. But the 0 came from the factor 2x squared, and the power on that was 2. So the multiplicity on that was 2. And remember, odd multiplicity crosses. So we're going to cross at 3, and we're going to cross at negative 3. But an even multiplicity is where you touch and turn. So we're going to touch and turn at x equals 0. Let's import all this information onto the graph. We have an x-intercept at x equals 0. It's already there. But because its multiplicity was even, we know the graph is going to touch and turn. I'm just going to put TT for touch and turn. At 3 and negative 3, we also have x-intercepts, but they're going to cross there. So let's go locate 3 and negative 3. 1, 2, 3. 1, 2, 3. 2 x-intercepts there. And we know that both of them are going to cross, so I'll put a C for cross. All right, we've got everything we need. Now, I'm going to sketch this. I know some of you are going to say, but how do we know? And I'll explain in a minute. So let's start drawing the graph. I need to start low and then cross through here, so let's do that. At some point, I'm going to have to turn around, touch this and turn around. Now, the question some of you are going to ask is, how high does this go and when do we know to turn around? The answers to both of those are calculus questions. So without technology or calculus, we don't have the wherewithal to know exactly where this graph is going to stop, turn around, and come back down. So for our purposes, you would simply just have to do it somewhere. So let's touch. We didn't touch anything yet. Let's have our turn and come back down here. Now remember, we're not going to cross here. We're going to touch and turn. And when that happens, you kind of flatten out just briefly. And now I have to do the same thing. Now I have to continue. I have to turn around, at some point turn around and come back down across this. But also remember that we have y-axis symmetry. The left and the right half are mirror images. So all I have to do is mirror what I did over here. 1, 2, 3 turning points, y-axis symmetry, correct y-intercepts, intercept, correct x-intercepts, and correct behavior on the x-axis, where it crosses versus touches, and correct in behavior. The only thing we couldn't really nail is how high do these get before they turn around, but again, that's a calculus question. We're going to take a look at one more. Actually, we're not. What we're going to look at in the last video is how to reverse engineer this process.